Hello everybody, it is time for another video. Now this one, I'm afraid the topic could be a little bit more subtle, but I'll try to tie it in to what we had already been learning about probability, okay? So the topic, as it would be officially called, is random variables. And what I'm afraid of is that sounds real complicated to people who've never heard it. Uh, you know, Variables is what I think makes algebra intimidating to a lot of people. Over all my years of teaching math, I've heard so many people say that they're fine with numbers, but as soon as you put letters in math, then they get really confused, and that's kind of what this is like. But I'm going to try to have it not be as complicated as it may sound. I'm going to do my best for that. So to do that, let's take stock of what we did before, and then I'll tell you where we're going to take that now. Okay, so here's the kind of thing we did before. We had a probability experiment of some kind. I'm going to use flipping a coin because that's an easy example. Everybody knows what a coin is. Everybody knows what a coin flip is. Okay, and whenever we have a probability experiment, the sample space is every possible outcome of that experiment. Okay, everything that can happen. So when you flip a coin, we could say the sample space is heads, tails, and I guess if we were really going to get creative or realistic, we could say the sample space was heads, tails, and then the coin falls off the table and gets lost or something like that. Okay, but to keep it simple, we're just going to say heads and tails. Now, here's what the stat cat has to say about that. Uh, Statistics is very mathematical. Okay, I think it can be very complicated, even in this class. And if you go beyond statistics in this class, it's very complicated. So the StatCat says we need something more mathematical than just the words heads or tails, because those are words, okay? And we do math with numbers, all right? So that's where we need to go, according to the StatCat. That's what he has to say. So let me translate this same situation, a probability experiment of flipping a coin, and I'm going to make it a little bit more mathematical with numbers, okay? So here's what we're going to learn now. Let's use the same probability experiment, flipping a coin, but I'm going to introduce something called a random variable, okay? So I'm going to say X is a random variable and it signifies an outcome of the probability experiment. Okay, and I'm going to define my numbers this way. I'm going to say if X is 0, that means the outcome was tails, and if X was 1, that means the outcome was heads. Now, there's nothing entirely special about those numbers. I could have said if X was 1, that meant tails, and if X is 0, that meant heads. I'm finding a way to make it more mathematical and have the outcome of the probability experiment be a number. So we define it in a way that it's now a number. Okay. All right. Now, so that's what all a random variable is. They're just numbers that are matched to the outcomes of a probability experiment. All right. So if I say X is 0, that means that the coin was flipped and it turned up tails. Okay. It's probably a little weird for most people because if you were just flipping a coin uh, to see, I don't know how football works really, but I think they flip a coin and it decides who gets the ball first or something. I don't know. If I'm wrong about that, I'm sorry. But, I'm sure that in a football game, if they flip a coin, they don't say the random variable turned out to be 0, so this is what happens. But in math, since statistics is a highly mathematical, highly technical field, that's the way that we need to do it. Now, so here's the kind of thing that we might say to express the probabilities. We might say the probability of the random variable x being 0 is a half. What does that mean? How are you going to think about that? That means the probability of tails is a half, okay? That seems weird, but that's all it means. Okay, that's how you would understand it. And what does P of 1 equals a half mean? Well, we said up here if x, the random variable, the outcome of the experiment, was 1, that meant heads. So if I say P of 1 is a half, that means the probability of a heads is a half. Not that complicated, really. So, like so much in math, you just have to know how to read the symbols and like translate it to your own way of thinking. Okay? So when I see these, that's what goes through my mind, and that makes it a lot easier than I think it looks on paper. Okay? All right, so that's where we get started. Now, let's see an example a little more complicated than that. So here I have some data, and I got this from our textbook, but whether it's real or not, I don't know. But it's realistic data, okay? And we're going to use it for example. But it says the data given below show the number of overtime hours worked in 1 week per employee. So they tabulated the data or surveyed the employees or looked at the records or whatever. And there were 6 employees that worked no overtime and 13 employees that worked 1 hour of overtime and 29 employees that worked 2 hours. You get the idea. That's what that means. Now, here's how we introduce the concept of a random variable, and we're going to put together something called a probability distribution. All that is, maybe that's another complicated sounding word that adds a factor of intimidation to this, but a probability distribution is just a table or a graph that gives the information on the probability or the odds of every outcome. All right. So like here, our random variable is x, and that stands for the number of overtime hours. And then right here, P of x is the probability of x being that given numbers. So now, when I encountered this problem in our textbook, the table was blank, and we were supposed to figure out all these probabilities. But let me show you how I did it. So here, like no overtime hours. What's the probability if you just randomly selected an employee? You know, you just picked one out. You don't know who they are. What's the probability that they didn't work any overtime? Okay, so that would be P of 0. The way that we would calculate that is the number of employees with no overtime divided by the total number of employees. That's the probability of just randomly selecting that employee that didn't work any overtime. Now, it turns out there were 6 employees that didn't work any overtime, and I counted them up. 6 plus 13 plus 19 plus 50. There are 191 total employees. So the odds of just picking that random employee out who didn't work any overtime was 6 over 191, which is about 0.031 as a decimal. So that's why this number is 0.031. So that's how you can look at a probability distribution. The random variable is going to be whatever number that corresponds to the outcome of a probability experiment. Here we pick out a random employee, and the outcome is how many overtime hours they worked. And there's a certain odds of that employee having any of these numbers. And then down here, P of x, that's the odds of that randomly chosen employee working that many hours of overtime. So you got the random variable and the probability that the random variable take on that number. All right. Now I did all the others the same way. Say, for example, P of 1 was 13 over 191, meaning the odds that a randomly chosen employee worked 1 hour of overtime. Well, there were 13 such employees over 191 total, and that turned out to be 0.068 in a decimal. That's why this is 0.068. So that's the concepts together of a random variable and a probability distribution. Okay? It might take a little while to sink in, but you know, if you study it enough, I'm sure that it will become something that you can accept. Now, I did that in the same way for all the other values of the random variable. Okay, 0 hours overtime all the way through 6 hours of overtime. So now that's one thing that we might do, is construct a probability distribution based on some data that's given. Okay. Now another thing that we might do is, in math we often like graphs because they convey a lot of information, and even among mathematicians and scientists, they are visual, and they can understand things better if they see it in a graph or a picture of some kind. So we might graph the probability distribution. Now I drew this by hand and I can't say that it looks real great, but I did the best I could. And so x here is the random variable, 0, 1, 2, 3, 4, 5, 6. Those were the hours of overtime, right? And then vertically, how tall each bar is the probability of x, the random variable, being that number. So look at it like here on the graph. So 2 hours of overtime, and that bar goes up to, it looks like maybe a little more than 0.15. So that's saying like according to the graph, the probability of any randomly chosen employee having worked 2 hours of overtime, it's about 0.15 on my graph, as best I can tell. Well, let's go see. So what was probability 2? It was 0.152. So that's what the graph's telling us. But we also get to see that there's a shape. It looks like most likely the employees are going to be somewhere between 2 and 4 hours of overtime. Okay, maybe skewed a little bit heavier to the right. There's a little bit more probability of 5 and 6 than there is 0 and 1. But anyway, that summarizes what the random variable is for every possible outcome. Okay, so what do we learn here? What a probability distribution is. We can calculate any individual probability the way we would have done it before we learned what a random variable was. It's just we're going to have to see a random variable on top of all this. Okay, it just stands for the numerical outcome of choosing a random person at this workplace, and the outcome being how many hours of overtime they worked. Okay, now next thing, we need a probability fact. All right, and I don't know if I've talked about this one before. I'm not sure that it's come up, but it's a fact. It's one of the basic things about probability. The probabilities of all outcomes in any sample space always add to 1. Now, let me use the coin flip experiment again. Flip a fair coin where it is 50-50 that it lands on heads or tails. Sample spaces, heads and tails. Now, if it's true that the probabilities of all outcomes in a sample space always add to 1, if I take the probability of getting a heads and I add the probability of getting a tails, that should add to 1. And probability of getting a heads is 1 out of 2, plus probability of tails, also 1 out of 2. And that does add to 1, but that's always true for any sample space. So like if you add, so here's the whole sample space here in this one, overtime hours, 0, 1, 2, 3, 4, 5, 6. If you add these probabilities together, then you'll get 1. Okay, it's always true. Now, let's say that we have an incomplete probability distribution, all right? Here, though, in this example that I give you, I don't want to say what the 3 is, or the 4 is, or the 5 is, or the 6 is. It's just that's the random variable. There's some kind of probability experiment, and with every outcome, it's either a 3 happens, or a 4 happens, or a 5 happens, or a 6 happens. You can think about it like this one up here, where you choose a random person from this workplace, and the outcome is how many hours of overtime they worked. Okay, so an outcome of 4 means that, or a random variable being 4 means that that randomly chosen person worked 4 hours of overtime. Okay, so here we see that as the same thing. It just doesn't, like, there's no information given about what those numbers mean in terms of the outcome. But the probability of the outcome being 3 is 0.19. For the probability of a 5, 0.27, and for 6, 0.26. But the probability of 4 is not given. Now, in the probability distribution, the whole sample space is listed. So getting a 7 is not one of the possible outcomes, and getting a 1 or a 2 is not one of the possible outcomes. These are all the possible outcomes, all right? So, well, say we're just missing one of those values. Can't we use this fact that the probabilities of all outcomes in a sample space always add to 1? So we should be able to use that. So like the probability of getting a 3 plus the probability of getting a 4 plus the probability of a 5 plus the probability of 6, that's got to be 1. And I know some of these values. I know that the probability of a 3 is 0.19. I don't know the probability of a 4, so I'm going to just leave that as is. The probability of a 5 is 0.27, and the probability of a 6 is 0.26, but that has to add to 1. So next thing I did is I got these numbers, 0.19, 0.27, 0.26. I added them together, and they make 0.72. So now I'm down to 0.72 plus the probability of getting a 4, whatever that is, has to equal 1. And in order to solve for that, I subtracted 0.72 from the other side, and the probability of getting a 4 is 1 minus 0.72. Turns out to be 0.28. Okay, so that's what I needed, 0.28. And that completes it. Now I know the probability of every outcome in the sample space. Okay, so well, I hope you see from this the whole picture, what random variables are, how it ties into what we did before, and then how we're just taking, the same kinds of situations in math and everything, and we're just making everything be a number now, instead of words like heads or tails and that sort of thing. But the rules really haven't changed, and how we do the math really hasn't changed either. We just have a slightly different understanding and a slightly different way of thinking about it.